Hybrid Life 3. So this is a session that we started organizing a couple of years ago, Alife 2018. Here's the hashtag. You're going to be able to find on Slack in case you have extra questions after the session as well. If you want to put faces on us organizers, here's a quick slide with, with us. In general, like when it comes to themes and, general ideas, what are we trying to, propose? What are we particularly interested in? So the Alife community is generally quite broad. There are many topics being covered. So what we are trying to focus on in particular is, I guess, the intersection, or should I say like the intersections, like plural, that you might find between the study of biological and artificial systems, artificial and cognitive, cognitive and biological, on all three of them together. We are particularly, I guess, we are then, I guess, a bit more broad when it comes to the type of approach. So thinking of, what theories might be of interest, like at different, to explain different intersections, or what kind of intersections we might be dealing with. So are we talking about the combination of two or three of these things? So are we trying to talk about the interactions that you might find between different elements? A little update since last year, which I guess was probably like the main highlight by some of us, the organizers, in particular Lana and Olaf, who were in charge of organizing this fake live recognition context, which was a challenge where you were given some different time series, XY positions of different things, different objects, different animals, different whatever you might think they may ever be. You see a couple of examples here at the bottom, and your task at the time was to decide whether they were coming from living or non-living systems. The challenge was quite a success. Here I'm just reporting a couple of articles you might want to read in more detail, and the winners, Christine and Tom, who may or may not be here now, but yeah, you should go and read about their results. I mean, the challenge was quite cool, especially non-trivial. If you look at this, the living system is the one on the left, and the one on the right instead, I think, is coming from, don't remember now, but yeah, not living, like by any sort of definition. Right, so very general, I guess, perspective that I wanted to give about this special session. We're gonna have a list of, 6 talks, starting with mine, and I just listed them on Slack rather than reporting them here, like trying not to be too redundant. So I guess I'm just gonna get started with mine. Right, so a bit of an outline here. I'm going to try to give a very brief intro to the idea of the what governor and what it was used for in cognitive science, what it can still be used for in cognitive science. A very brief, I guess, overview of predictive coding and active inference theories and why I think they might be relevant for the study of cognitive systems. Then I'm going to try to make a connection, which was the main selling point of this manuscript. And then I'm going to try to draw some conclusions of what this exactly may entail and how it should be particularly, I guess, understood. So the what governor, it has been used in cognitive science at least for the last 20 to 30 years as a possible metaphor, as a possible example of systems that we might want to study and that are in some ways similar to biological systems, to cognitive systems. The discussion is very long. You're going to be able to find a bazillion papers on, supporting or, being against this view. You're going to be able to find some references in the manuscript as well. The idea was essentially to try to find something that could replace the computer metaphor, the digital computer metaphor that people are so keen to use when they try to study cognitive systems. The questions that can be asked are quite different in a way. You might want to ask whether we could think of the brain as being a computer as being a governor, or if we should just think of them, when I say them, I mean brains, as behaving like a computer or behaving like a governor. The history of this system is quite long. It goes back to James Watt, who first used it to essentially control steam engines and, you know, essentially, you know, power through like the first industrial revolution. It was first studied formally by Maxwell, Maxwell, 1868. The paper was then rediscovered by Wiener, who used it as an example for cybernetic systems and examples of negative feedback, examples of teleological systems, examples of systems with a purpose. They were then criticized by Jonas in 1953 as being a clear example of people confusing the purpose of an experimenter using a system and the purpose of the system itself. So Jonas was actually arguing that biological systems have some intrinsic drive that is not captured by the word governor. Ultimately, I guess that it became quite famous in 1995 when it was used by Van Gelder as an example of, as an alternative to the computer metaphor that I mentioned earlier. So here's a little video. I'm not going to play it all, but I thought that it was quite nice to have something going if you've never seen the system actually working. So steam engine on the left, governor on the right. You can see that if the person actually goes and plays around with the governor, the velocity of the steam engine is actually changing. The idea is quite simple. I'm going to try to give a very general, I guess, understanding of how the system actually works in case you're not familiar with it. You have a couple of weights attached to two arms, which are then attached to a vertical rod. This is then linked to the valve of a steam engine, such that every time the valve is fully open, this makes a gear that is attached at the bottom of this rod rotate, so that the two weights start rotating around the vertical rod. When they rotate around, they actually close the valve. So the idea is that you are going to be able to find in the limit the right opening for the steam valve, so that the stability, so that the angle of these two arms is not moving at some point. You're going to have some fluctuations, so the valve is going to open and close for a while until hopefully it will stabilize. It's not necessarily trivial, but it is something that can be studied quite analytically. Here I have some equations just to show that I actually did equations, but I'm not going to go through them because I don't have the time to explain everything. In particular, I guess the mathematical side, since I'm interested in the conclusions that can be drawn from that. If you have some questions, just ask me later on. I'm very happy to go through the mathematical formulation. So active inference and predictive coding. So what's the main idea? I guess that for me, it is to try and find some sort of mathematical treatment, mathematical theory that can connect different theories, different ideas from different research areas. Something, for example, coming from control theory as negative feedback, something coming from estimation theory, inference predictions, information theory, relative entropy, KL divergence, mutual information, something that comes from non-equilibrium dynamics, so the study of systems that are far from equilibrium from a thermodynamic perspective, ideas from self-organization, self-production, autopoiesis, self-maintenance, homeostasis, so on and so forth, trying to find some theory that can actually capture all of these different ideas. To give like a very general perspective, I'm going to try to start with a couple of very basic claims, which are both instrumental. This is something I want to make clear. I'm not trying to say that there's any ontology that I'm attaching to this. In a sense, I'm just trying to say I can write down some equations and I can say that these equations are useful to study this process. In particular, perception might be usefully studied using processes, using ideas from Bayesian inference. Now, there are a few books about that. Hopefully, I don't need to convince you that this might be a useful angle. Second claim is that behavior action can be studied through ideas of optimal control. Again, this is just an instrumental claim in a sense that I'm just trying to say there is a tool, control theory, that can be used to study something, behavior action. The general intuition, I guess, behind the maths, which I'm not going to treat in detail, is that you can write down problems of inference and problems of control using perhaps the famous, I should say, Bayes theorem, which you just find here on the right. The thing is that most of the times in practice, you cannot compute the posterior probability that this theorem actually gives you as a combination of likelihood and prior normalized. So people actually come up with an approximation that comes from statistics, which is called variational free energy. The idea then, and here I just try to make it graphical, is that perception will be something that reduces a bound, like something that is an upper bound, something that acts as a squashing term onto the posterior that we want to estimate. And action is going to be something that actually changes your observations. Once you reduce this to the minimum, you're supposed to have something that actually is explanatory or in some way actually helps you to study a system. Right. So the thing is that this theory has been proposed for, theories of life, theories of the mind, and it had also been proposed as simply some sort of mathematical framework that actually might capture different aspects of theories, as I was proposing just a few slides ago. I'm particularly focused on this last point with applications to minds. The schematic, I guess, if you're interested in applying a theory of this kind, and in particular to the example we have here, is come up with something like a generative model, which is a model that describes how your data might be generated. Find the variational free energy function that actually approximates the posterior you're trying to estimate, combine them together, minimize that function, come up with some equations, which here I call recognition dynamics. And in the paper, they just turn out to be the equations of an engine. Attach them to a governor, and what you get then is a system that is actually controlling the engine that you just derived. For a more Alife, I guess, angle, you could think of these equations that I just derived as something like an agent. You could think of the governor itself as an environment, and you could think of the scientist as the one coming up with this extra equations to actually define the agent. Notice that here an agent environment might be slightly different from what you expected, but this is something that would be nice to discuss either during question time or later on. If you want to see the equations, again, here's what I used in the paper. Again, not going to go through the details too much, just to report again that there is some maths in there. Take a generative model, take a free energy function, combine them, come up with a gradient descent on that function, and then with a couple of assumptions that are quite standard and that I guess are fundamentally related to some treatments in non-equilibrium thermodynamics, although I didn't go there. You can get something which is exactly, if you don't trust me, just go back and check the previous slides as soon as we are done. The last equation there is exactly the equation that we get from the engine that is attached to the governor. The thing that I want to focus on, however, is whether the maths that I did there has actually any true meaning, in a sense that people say, oh, brains can be seen as predictive engines, brains can be seen as engines that are, inferring things about the world. Well, that's all great, but, what does that even mean? If I try to use the same language here, does it mean that the governor is predicting something about the engine? Does it mean that it has a model of the engine? Does it mean that the engine has a model of the governor, or the other way around, or any sort of like crazy idea like that, which I tried to summarize with a sketch here. Does it mean that the governor has a model of itself, that it infers itself, that it infers the engine? Does the engine infer? What does this even mean? So as an example, I guess that I quite liked, Ceres was a dwarf planet that was discovered in 1801. Then people lost track of it and basically asked scientists at the time to try to come up with predictions on where they would be able to find this dwarf planet back. Basically, half of the year it spends behind the sun, so it's not really easy to spot. So the problem was actually solved by Gauss, who at the time used, probably for the first time officially, the least square method, which you might be familiar with from statistics. And the thing is that he predicted where the planet was going to be. Now, the question here would be, if I take the same approach that I just, tried to take for governors and engines, does it mean that Ceres is actually predicting where the sun is? Does it mean that the sun is predicting where Ceres is? Does it mean that Ceres is predicting its own trajectory? Does it mean, what does this even mean? The only thing I can say here is that there was a scientist, Gauss, who actually came up with a theory, made a prediction, found the dwarf planet. So a better scenario for me is to try and, define who's predicting what, who's inferring what, based on, the job made by a scientist. So I, as a scientist, wrote down some equations such that I am predicting the velocity of this engine. I am predicting the angle of this governor. I am predicting such and such. The thing here that I want to conclude with, hopefully triggering some questions afterwards, is the difference, the main difference that I see between, using a tool, and again, I'm probably just reinventing the wheel, because this discussion has come out probably for 2,000 years in philosophy. And in a way, what I'm trying to say here is just that the same questions that people have asked for different frameworks should be asked for this predictive coding active inference framework that people are trying to use to study brains as well. So if I take this framework, this active inference framework, you can see some other names here that it goes by. And I try to use this framework to do some cognitive science to study brains. What exactly am I saying? So there are two routes that I see. One is purely ontological, in which you say, oh, brains are predicting something, which is a very, I guess, popular way of explaining this framework nowadays. But in the same way, then you will have to ask what Ceres is predicting when it's actually rotating around the sun. You will have to ask what an electron is predicting when it's actually, orbiting around some nucleus. This is risky to me. Something that I guess is more safe, and I'm just going to report a fairly recent discussion on this that is quite Alife related, is to take some epistemological stance, like take a step back and say, look, I have a bunch of frameworks, I have a bunch of ideas, I have a bunch of specific tools that I may use to study brains. Are brains predictive? I don't know. Am I predicting something about brains? Well, hopefully so. I mean, we've been able to predict, so far we are trying to predict even, a galaxy colliding with each other up to 5 billion years away. Does that tell us something about what the galaxies are doing? Well, in a way, it helps us predict their behavior, which is, I guess, what most of us are interested in at the end of the day. Acknowledgements to my two co-authors, to Inma Harvey, Filippo Torresan, and Adam Shea, who gave me some great feedback at different stages, at different steps of this manuscript. To my funding agency, JSPS, and to the grant who supported this work. Few contacts there, and well, thank you very much. Now, as a general, I guess, question, should I stop sharing? Is that the best approach? Or should I keep?
Whichever. Yeah, and if somebody else has like a clarifying question on the slides, you can always start sharing again. It's easy.
Yeah. Thank you. There we go.
Questions, anybody?
And I think Matthew Egbert's group may have some questions. He's asking in the Slack where questions go. So I'm gonna say questions should be posted in the chat if possible.
Can anybody hear me? I've got a question if it's time for that now.
Yeah.
Manuel, thanks for the talk. I want to ask
for
the
everybody,
question that you said
people can raise. There else has a question, I do, but maybe somebody else has one.
Go ahead, Matthew.
All right. Well, I'll go ahead and throw in a question.
Sorry.
Or no, we got someone.
Yeah, Manuel, you said that you had this sort of counterintuitive way of thinking about the Watt governor as the environment rather than the agent, and you said you might explain that in the Q&A part. Would you mind explaining why you had that way of dividing the system up into agent and environment rather than maybe a more intuitive one where the Watt governor would be the agent?
Perfect. Thank you, Matthew. So this is something, I guess, that is not, that is probably going to take some more unpacking, I guess, even on my side, because I feel that there are some questions that are a bit unanswered as of yet. So I guess like in practice, it was simply because this was the easiest way for me to get some, like the equations that I wanted. It was much easier to derive, let's say, this side than it was to derive the actual governor as a process of prediction error minimization. The thing is that there are two ways to see this. Either from the angle that essentially if there is an asymmetry between the governor and the engine, well, the asymmetry must work both ways. So it is, I guess, just a subjective choice at the end of the day, which one you prefer to see as an agent. This would be like the more evasive answer. I guess the one that I'd like to explore more is whether there is some more meaningful sense in which an engine can be seen as trying to regulate itself, whatever that may ever mean. Because I guess that is not particularly intuitive once I guess I think about it like a bit more deeply. What it means for a governor to say, you know, that is going to try to come up with an angle such that, you know, the steam valve is open in a certain way, blah, blah. It is much easier, I guess, for me to see the valve opening as an action itself, rather than it is to, you know, think of an angle like some, you know, displacement measure at the end of the day, just some position change. It is much easier to see the valve as being an action than it is to see the angle. So this, I guess, may also come out from the fact that, and probably this ties together with my first half answer. Like if you go through a dynamic analysis of this system, which is, let's say, step 2 that you find in a standard book, you can see that the angle and the angle of the two arms and the valve opening are essentially related by a relation that is called non-uniformity of, oh God, it's in the paper now, non-uniformity of performance, which simply means that, you know, the two of them are perfectly interchangeable. So there is, up to a constant, there are quantities that are perfectly interchangeable. So in that sense, to me, they become, you know, just an extra, like one more reason to say, you know, it could go the other way around. Like whatever way you choose may actually be sensible in some sense. But yeah, there is stuff to be answered yet. Should I go with a question I just found on the chat? Yeah. Right. So how much is it a problem?
This is me, Manuel. I was saying that because I think maybe a little bit of it is a problem that prediction, there is a mathematical way we would use prediction where it doesn't mean in Inman sense predicting something to someone, but it in the same way we'd use inferring to mean that you can make a relationship between something. So how much do you think it is a problem of language, and do you think that that's is that an issue?
So it is partially a problem of language to me, because there are many different, I guess, takes on what a prediction may be at the end of the day, as you were just, briefly, pointing out. It is also a problem that, so I'm trying to write another paper, like a more extensive version of some of these ideas with some friends. And I guess that one of the words that one of the guys came up with was something like pan-inferentialism. So how much are we trying to just, attribute processes of, inferring something, predicting something to any system? And is that useful? Well, I mean, in a way I could write down potentially any physical system as inferring something. The question then, I guess, becomes what you just asked, like, is it inferring that for itself, or is it inferring that for somebody else? So at that stage, I guess you might take either positions. I'm not particularly concerned about any of the two, but I guess that for me, like, the main issue is when people try to use prediction in one way, which is, the physical way. Like, as a physicist, predictions can be made about such and such, and then they transform it magically into, so they start from a non-ontological perspective, and then the ontology comes out, for free, which I don't see. Like, I don't see how me making predictions about something means that something is making predictions about something else. That step, like the extra step, is where the problem is for me.
Yeah.
Lisa, did you have a question? Oh, you can continue if that was.
Yeah, I can have a question. So, sorry, my internet seems to be a little strange right now. My background is more like I was super into cognitive science until maybe like 2012, and then fell off the boat. So this like predictive account of things is a little bit new to me. But a lot of the questions that you're asking sound kind of the same as, like, where does computation happen? Where does cognition happen in systems? So I guess it was making me think, like, what's special about prediction? How are these questions different than those questions of just like, where is computation or cognition happening in general?
Thank you. I mean, that's a great question. So I guess I would go two routes. So one, potentially just it's just a matter of semantics, in a sense that these terms come from different research areas. So computation, I would say more like information theory, and early like computation theory back in maybe like the 40s. And inference and prediction, I guess, come from more of a statistics angle. So that could probably, go back to Gauss himself, and I guess beginning of the last century, probably with Fisher, Person, and a few other people. Sometimes people do this mean the same thing when they use, for example, inference, or when they use computation. The trick might be at times where people consider perhaps prediction as something like future oriented, that is not necessarily there with the terms computation itself. But to me, I guess, it's just a matter of, what field you were most familiar with. If you ask people like Inma Hardy, I guess she's gonna say that the two of them are essentially problematic in the same ways, which I kind of agree on. Like, there is nothing like that is going to make a system better when once you call computation something like inference or prediction. The same issues will be there. The same questions will be there.
Cool, thank you.
Hi.
Other questions?
Yeah.
Is there time for more questions?
Oh, do we have more time?
Yeah, we have plenty of time.
Oh, Dobromir, please go.
Yeah. Okay, so I'm trying to imagine what would happen if when you put this whole scenario in a situation where these separate parts are not anymore tuned to each other, so to speak. So this thing works because in advance, the arms were set to be the right length. So there are lots of things that have to be tuned very carefully. There's kind of this implicit internal modeling where it has to follow the right dynamics for it to work. So let's say that, I don't know, it breaks. So like one of the, or you just couple it to a different engine. Would you say that it does not predict anymore, or it predicts incorrectly, or it's hard to think about it anymore because the equations don't make sense anymore?
So again, like very good point. I'm gonna try like to connect it to another example that I had at ECAL 3 years ago with Breitenberg vehicles and a very similar setup. So pair like a bunch of equations for a Breitenberg vehicle to an environment. As you say, as soon as you detach them, the thing, of course, is not controlled. It is not, you know, if we are talking about Breitenberg vehicles that are not moving towards or away from the light anymore, the system stops making sense. Then the question, I guess, becomes, as you were saying, like, is the governor in this case still making predictions about something? And there, I guess, lies one of the main issues. Because you could go, I guess, both ways. As you just mentioned, I guess there are two ways to go. One in which you might say, yes, it is still making predictions and they are absolutely nonsensical. And the other one is, oh, it's not making predictions anymore. And I guess this highlights like this ontological versus, instrumental questions that I was asking. Like if you go purely ontological, you will have to say that it's still making predictions, but they are nonsensical to you, but perhaps still make sense to the governor, to the engine, sorry, whatever that means. Or you might just go the other way around and say, well, you know, instrumental, like an instrumentalist say, these predictions make no sense to me because the engine speed is not being controlled anymore. Therefore, there are no predictions that are sensible being made there. So I guess both takes are, you know, correct. I guess as soon as you point out, you know, the perspective of whom you're taking at different stages. And again, I think this is a great point to highlight the sort of confusion that people make when they talk about predictions for predictive brains and predicting things.
Cool. Awesome. All right, I think we can move on to the next speaker. That's.
Thank you very much, guys.
Very nice. Okay.
Did I,
We have